everybody. My name's Lisa Bastarache, and I'm a data scientist and now a new associate professor of biomedical informatics at Vanderbilt University. And I've been lately calling myself a phenomicist. Maybe that's a little bit corny, but really and so I might drop it depending on your all feedback. But really what I do every day is, I have two jobs. One is I work with physicians and also bench scientists to try to use medical record data in conjunction with our biobank at Vanderbilt to answer the questions that they find important. So a researcher might come to me and say, I'm really interested in progression of sepsis if people have this particular type of HLA type. And I'll meet with them and I'll assess the types of needs that we have from the medical record to extract that type of information. And the second part of my job, which is complementary, is to develop methods, generalizable methods, to extract phenotypic information from the medical record. So I want to tell you a few things. I've been doing this for over 10 years now, and I want to tell you a few things that I've learned along the way in order to maybe save you guys some time if you're endeavoring to do this type of stuff. So first of all, I didn't want to presume familiarity with the medical record. I will say anybody who's looked at these medical records, there's an idealized vision that you might have of what the medical record is. It contains notes that doctors are writing probably while you're in the office sitting with them about what your complaint is that you come in and discuss with them, the types of medications that you're on, maybe a physical exam, some measurements, and then a conclusion. And those types of notes do exist in the medical record, these narrative texts. But in addition to that, there are also a number of other different types of notes. For instance, there are discharge summaries when you go into the hospital and then you're let go. There are problem lists, which are sort of a running list of the types of issues and medications that you're taking. There are clinical communications, at least at Vanderbilt and probably most medical centers at this point, have a way of electronically communicating with your doctor. So patients can write to their doctor and say, hey, this cough isn't going away and I finished my antibiotics, what should I do? All of these pieces of information can be used in mind for phenotyping. And the narrative text of the medical record really does contain much of what is known about the patient from the perspective of me, the data scientist. On the other hand, this is very difficult data to use. I have here, I guess I'm contributing to the problem here. Well, actually, maybe it's fitting that this one screen is blank so you can't read part of this text, because usually the information that you get from this is really not clean at all. There's a lot of things that are elided. There's a lot of fuzz. There's a lot of contradictory statements. For instance, somebody may have a history of present illness here where they're talking about this raging rash that they've had for 2 weeks. It's all over their body. And then in the physical examination, it'll say skin, clear, no sign of rash, right? Which one is it, right? So this type of, my background is actually in natural language processing, and I love this type of stuff. I love writing parsers. I love NLP tools. But a lot of the best efforts can be really defeated by the complexity, noisiness, and sort of like the frank, untrue statements that are contained in this medical record. A different type of phenotypic information that I leverage a lot in the work that I do is structured data. And that includes, most prominently probably, ICD-9 and ICD-10 billing codes. Now, these are codes that are used to basically extract money from you, the patient, and put it into the doctor's pocket in the hospital, et cetera, right? If you go to a doctor and you complain about, and you cough in their office, basically, you will probably be billed for that cough. ICD-9 and now 10, which is what people are using now, can bill for different symptoms that people have as well as diagnoses that doctors make. And so most medical, I think basically all medical records will contain these billing codes. And they are a very helpful sort of computable abstraction from a lot of the content that is in the medical record itself. There's also other types of structured data such as lab data. So probably all of you have gotten at least one, maybe even hundreds of blood draws for hospitals, maybe to get your complete blood count or a differential. So all of those measurements are typically part of the medical record. And I'm going to be talking about how to manipulate these types of data elements and do some science with it. There are also CPT procedure codes. There's prescription and medication information, which I'm not going to talk about, but it is a pretty prominent part of the medical record. So one of the main reasons that I've spent so much of the last decade doing research like this is that we have something at Vanderbilt called BioView. And this is, I know that at UCLA, you have a biobank as well, where you have medical records that are linked to blood samples. So with that setup, you're able to actually pull blood, put it on a chip or sequence it, and then look for correlates for phenotypes that you can find in the medical record. So the game is then, can you take the medical record and extract phenotypes that you can use for genetic research? And I'll show you what is actually probably, I would say that this represents the first type of phenotyping that was done in the medical record, and it's a process that still exists today. This here is the answer to the question, can you give me everybody who has hypothyroidism in your medical record? It was an algorithm that was developed in the first round of this group called eMERGE, which was at the time 5 different sites that shared data, and genetic data and medical record data, and they studied phenotypes together. So this algorithm, which I apologize if you can't read, I'll go over some of the highlights, is an attempt to sort of make into a computable format what the definition of people with hypothyroidism in the medical record will look like. And it contains a number of different elements. First, for cases, they required that the patients had at least one ICD-9 billing code for hypothyroidism. They also required that they had an abnormal high TSH or low FT4, which is indicative of hypothyroidism. They also required that the patient is on Synthroid, levothyroxine, or some other medication to regulate their thyroid. And then there's a bunch of exclusion criteria, including exclusion criteria for control, so people in cases, so people who are pregnant and have thyroid issues, or people who've had thyroid ablation, they're excluding from their case definition. And then so on, they used keywords, so they did a little bit of NLP for this algorithm. They also excluded people on the basis of other types of medications which may mess your thyroid up. And that was obviously, you look at this, is very complicated. It was a lot of effort to do across 5 sites, but this effort was rewarded actually by the discovery of a novel association with hypothyroidism in a variant near a gene called FOXY1. And it was one of these like really pleasing situations where this didn't drop out of nowhere. There were actually variants in and around FOXY1 that were known to be associated with thyroid cancer. So this study showed that it was also, there were variants near this gene that were also associated with hypothyroidism. So that was a happy, you don't always get positive results from GWAS, so it was really exciting to see that work across 5 institutions and to see that we had a portable algorithm to capture people who had hypothyroidism. But one thing that we observed in the process of creating this phenotype and others is that the ICD codes were really the core of what formed the definition of these phenotypes. And so in parallel to developing phenotypes like this, my boss at the time, Josh Denny, and I were working on developing what are called Phe codes. Phe codes are essentially just ICD-9 and now ICD-10 codes that are grouped together into clinically meaningful concepts. For the case of hypothyroidism, actually, there's really only one billing code that is important for hypothyroidism. It's this 244.9 hypothyroidism NOS. And so we map that to a code that's called hypothyroidism. For other codes, actually probably tuberculosis being the craziest one, there's hundreds of ways of billing people for tuberculosis. But ulcerative colitis, for instance, there's a way to build somebody for left-sided ulcerative colitis, then unspecified ulcerative colitis, et cetera. So we group those into one Phe code for ulcerative colitis. And for any of you who have experience looking at ICD-10 billing codes, there's just a huge proliferation of these types of billing codes, which makes condensing them all the more necessary. Anything that can happen to the left side of your body can also happen to the right side of your body, or both sides of your body, or they don't know. So every medical condition conceivable at least has, that can happen on one side of your body has 4 different codes basically. So this just allows you to condense these codes together, and we have this map that you just take the ICDs and you map them into Phe codes. We also...
Are the Phe codes ICD-9 as well?
So we made a really bad decision here. You'll notice that, and it was one that was really baked in by the time this method took off. So you will notice that the Phe codes look a lot like ICD codes, but they're a little bit different. It causes a lot of confusion. Probably what we should have done is put a P in front of them or something to delineate them. No, they are often, the ICD codes are often they look a lot like ICD-9 codes basically, but they are not the same. So good question, thank you. We also define these exclusion criteria for ICD codes. So if you're coming up with cases with hypothyroidism, you exclude people who have other disorder as a control. You don't include anybody who has a goiter, for instance. And another rule of thumb that we've come up with is to require that people have at least 2 unique days that they've had this billing code in order to include them as a case. That's just sort of a blanket starter rule. So using this is something that Josh and he pioneered. We could start running something called PheWAS. So that association that I showed earlier, based on FOXY1, that was associated with hypothyroidism, we can then take that one variant and ask, what other phenotypes are associated with this? Because we're just using billing codes, they're so lightweight, we can define 1,200 different phenotypes really rapidly. So what we found with the PheWAS for FOXY1 is that we reproduced the association with hypothyroidism using this different phenotyping method and also other thyroid problems like goiter. We also found an association that wasn't quite statistically significant with atrial flutter, which we later found to be a genuine association. But in doing this PheWAS over here, we actually inadvertently did this experiment, this is really the first point that I want to make to anybody who's going to be doing EHR phenotyping. We kind of inadvertently asked the question of how much did this really complicated algorithm help? I mean, how much more do you get out of it by coming up with all these inclusions and exclusions, et cetera, versus just using 2 or more billing codes? And the answer is, it really actually probably hurt more than it helped. I'm not sure if you can see it, but the super complicated algorithm, you get a p-value to the -9th, respectable, right, with an odds ratio of 0.74, and so it's protective of, this variant is protective of hypothyroidism. But if you just use 2 or more billing codes, you get basically the same odds ratio, and your p-value is to the -13. So in essence, what I think this taught us was that sometimes you can really overdo it. In principle, you can have this beautiful phenotype that you really feel proud about putting in your methods section. And yet, when you actually look at how that phenotype behaves, it's actually a little bit further away from where you want to go. So to analogize, I don't know if you guys saw this news story. It's a few years ago, really resonated with me. So some police in Pennsylvania somewhere released this sketch of a suspect who had actually robbed a bank. There was a woman on the scene who witnessed this and sketched down this, drew this face. They put it out on Twitter, and they were like hilariously mocked. Other people released sketches of the vehicle. But it turns out actually that a cop a district over looked at the picture and recognized him, and it turned out to be the right suspect. So this is another instance where, sometimes something that's a bit ugly looking actually does the job. And in my opinion, I think that you should always judge your phenotype or your police sketch based on whether it actually gets you to where you want to go. So along those lines, I want to say that part of this idea is to really rely on replication to start understanding what you're extracting from the medical record. And this is something that we've done a ton of work with in the Denny lab. One of the projects that we did early on, because I guess backing up a second, it's kind of a crazy idea to think that we can use billing codes from medical records to do genetic research. I mean, there's just very well-warranted skepticism that you could have about that. So what we did in 2013 is endeavored to try to replicate every association that was in the GWAS catalog using this method. And what we found is that for those that we were powered, we replicated 51 of 77 associations across a really wide variety of phenotypes, including different types of cancers, autoimmune conditions, hyperlipidemia, et cetera. And since we've gotten larger cohorts linked to genetic data, this replication rate is actually approaching somewhere in the 90s, maybe 92% or something. So it's a very robust method for replicating known associations. So next thing I want to talk about really quickly, though, is using lab data. I've been collaborating with some folks at the University of Michigan, including Matt Zawitowski and Josh Weinstock, who somehow doesn't have a picture of himself on the internet I couldn't find, so sorry, Josh. Or congratulations, Josh, I'm not sure which. And also Jeff Goldstein, who's at Northwestern University. So as I mentioned earlier, there's a lot of lab data that's linked to EHRs. And lab data can be a very, very powerful source of phenotypic information about patients. In fact, there's actually like 1 billion measurements that is present in the EHR at Vanderbilt. But there's a lot of trickiness to utilizing this. This slide here actually shows, though, how powerful it can be to move from a binary phenotype, like getting billed for hyperlipidemia, versus looking at measurements of LDL cholesterol. So the folks at Michigan, they're crack methodologists there, they came up with a new plot. And so this bottom part, the bottom blue part, is the GWAS for the phenotype that is binary. So whether people were actually diagnosed with hyperlipidemia. And the dots, the red dots are if they, using patients' average LDL cholesterol. So you can see that you get a heck of a lot more power to discern genetic associations if you use continuous variables, at least in this case. But any person who's a data scientist working with this data, when they think about, I should use lab data, there's immediately a ton of questions. One is, how do you summarize patients' data? This data actually occurs across time. Do you use the mean, the median, the min, the max, the first? Maybe that's a pre-medicated state, you get the first, or maybe you should rely on the outranges that are provided in these labs and convert everything to a binary, high or low. So those are all options. And then secondly, once you get a distribution of data, if you stick with the continuous variables, how do you normalize them? Do you just use the raw data? Do you use log? Do you do an inverse normalization? And finally, I just thought this is a really interesting plot. The context of these lab measurements is really important. So this is a plot here that shows the difference between inpatient and outpatient measurements of different labs. And you can see that something like troponin is really elevated in the inpatient setting, as well as C-reactive protein. Anybody have a guess why that is? Anybody know what troponin measures? Yeah, they're having heart attacks. So I don't know why people are getting measured troponin on the outpatient. It might be on a panel, but it's normal. When they're coming into the emergency room and they get admitted because they have chest pain, a lot of them are having a heart attack. So anyways, the context of these labs really matters. So then there's another question. Should I only use outpatient labs for this study? Should I use inpatient? So what we've done, and this really was led by the folks at Michigan and Jeff Goldstein, is we tried all of these combinations. And what we did is looked at, one, what was the concordance between what we found in Michigan and what we found at Vanderbilt? And then secondly, how well do we replicate known associations with these lab values? So I'm not going to get into the results because really the thing that I want to convey is that it can be very powerful when you have to answer all of these questions that are very difficult to answer in principle. I mean, can any of us really make a principled argument that the mean is superior to the median of these lab values? So in my opinion, in my experience, the best thing to do is to actually test this against things that are already known and look at how your variable behaves when you make these decisions. Second piece of advice, which I think maybe is timely because of this announcement of this new collaboration you're going to have with the medical center, is I find it incredibly valuable to talk to clinicians. So this is my friend Jeff. He gave me permission to use this enormous picture of him. I talk to Jeff almost every day lately because I've been doing a lot of work with labs. And I ask him questions like, what is ferritin and why is it measured, And he will tell me things that I would never have guessed. For instance, let's say I want to pull all the glucose labs. Well, there's like 20 different types of glucose labs. That's actually probably 50, right? There's glucose, glucose bed, glucose whole blood, there's 1 hour glucose, 4 hour glucose. So it's only by talking to a clinician, in this case a pathologist who really is involved in the production and interpretation of this data, that I can learn that I should probably not use the glucose bed because that's not really measuring what I want. So I just encourage anybody who's using this EHR data to really try to get in touch and make friends with people who are actually producing this data and utilizing it. And as a second and no less important point, I'm in biomedical informatics, and I work in the Center for Precision Medicine. That means that I'm ostensibly really trying to develop methods that could possibly help people down the line. And if I do develop anything that could help a patient, the conduit of that is going to go through clinicians and medical providers. So producing work that makes sense to them and that is in touch with the needs that they have, I think is of fundamental importance. Now I'm feeling preachy. My final point, though, is don't forget the patient. If you ostensibly want to help people in your research, and actually, I don't think that necessarily should be the goal. Like, I'm not making a normative statement there, right? There's a lot of interesting research questions. Basic science is very important. But if you're going to be practicing in the field of precision medicine, don't forget the patient. And I never see patients. I've been invited to go to clinics from a lot of doctors, and frankly, it just really intimidates me. But the next best thing is that I can spend a lot of time reading charts. So just sitting there, staring at charts, hands off the keyboard, which I've done a lot of. And I've done a lot of in the last year, and it's taught me a lot. So for the last part of my talk, I want to just discuss a case of something that I read in the medical record and discuss a method that I think could address some things that come up with this case. So this is an unusual patient who started at Vanderbilt, started going to Vanderbilt in 2006. He was in his 50s, 60s. And he presented with a cough, which is very common presentation for somebody of any age, really. But he got a chest x-ray and he was diagnosed with bronchiectasis. He then got his sputum cultured and it was found he had pneumonia due to Mycobacterium avium. And so he was put on loads of antibiotics, course after course, and he did have some improvement. But as was stated in a clinical communication, he was improved, but he wasn't well. And unfortunately, into 2008, he started getting worse symptoms, started getting really fatigued. He had coughing fits. They started waking him up at night. He was cultured again for Pseudomonas. And then for the ensuing 4 years, unfortunately, he sort of had a slow decline. He eventually got surgery because he had chronic sinusitis. And then at this point, when there are doctors in the room, they're like squirming. They know. But finally, in 2014, as a clinician, he actually went to a different doctor, and I can't tell why, reading the chart. He went to a pediatric pulmonologist, which is pretty interesting because these pediatric folks, they're primed to think more of a genetic etiology for symptoms, right? And so he gets a thorough history from this pulmonologist, and she asked, "Do you have any kids?" And he said, I've adopted 2 kids. So he has a history of male infertility. At that point, she gave him a sweat chloride test, which came back borderline. But that was enough to get a genetic test billed through the insurance company, and it turns out that he had cystic fibrosis, an atypical form of cystic fibrosis. And actually, wonderfully, this is a treatable condition at this point. Particularly atypical forms of cystic fibrosis have a really effective drug that this man went on and is still living in his 80s now, and he's retired. So he was able to actually get an effective treatment for these really chronic medical problems that he was suffering from because of this diagnosis. So when I present this case to doctors, which I've done a couple of times, they usually feel a bit horrified that somebody didn't say Pseudomonas, bronchiectasis. I mean, how did somebody miss this, right? Which is why I made these slides, because I think that we have to, before we get judgmental about this, recognize that this is one patient among 1.3 million at Vanderbilt. And among those patients, 160,000 of them have cough. That's 1 in 8. Very common symptom. And a lot of them have chronic sinusitis. And many of them have bacterial pneumonia. And bronchiectasis, which is not terribly common, still we have thousands of patients with bronchiectasis. And yet, in that entire 1.3 million patients, we only have 862 who have been diagnosed with cystic fibrosis. It's a rare Mendelian disease. And so no one single symptom is going to point you directly to cystic fibrosis. But if you look at the combination of these symptoms, I'm trying to move fast so I can get to the punchline here. If you look at the combination of all 4 symptoms, if you look at patients who have cough and chronic sinusitis and bacterial pneumonia and bronchiectasis, 50% of those patients have been diagnosed with cystic fibrosis. This is to illustrate the point that combinations of these phenotypes can be very powerful, and I think can be used as a way of helping to augment the process of diagnosis that clinicians are doing every day. So to describe a method that we've developed around this, I'll talk about another Mendelian disease that maybe you guys have heard about, Marfan syndrome. It's a connective tissue disease. Some people think Lincoln had it. I'm not sure if the jury's still out on that. People with Marfan's are typically a little taller than average. They dislocate their joints. They can, unfortunately, get aneurysms. They have myopia because of a problem with their eyes. So like many Mendelian diseases, Marfan syndrome is characterized by phenotypes that hit multiple systems, right? And there's a catalog for this. And if you guys haven't gone and looked at it, I think it's just I encourage you because it's so phenomenal. Started by Victor McCusick from Johns Hopkins, called The Online Mendelian Inheritance in Man. And this catalog has really formed the foundation of clinical genetics. It was started in the 50s, before we had the ability to look in the human genome at all. There were clinicians who were observing that there are people who had these clusters of symptoms that traverse through the generations in predictable ways. And so using the logic of Mendelian inheritance and very careful phenotyping of the patient, they were able to identify hundreds of these diseases before we had the capability of actually genotyping people and elucidating the genetic cause, which I think is a phenomenal accomplishment. And if you look at the things that were discovered in that era, and you think about how are genetics helping people today in the clinic, much of the use of genetics right now has come from knowledge that was built in that era. So for that reason alone, I felt really inspired to research how these folks think and think about ways as a computational person that maybe I could leverage their success and sort of augment their endeavor and initiative in the computational space with the complement of all this data that we have now. So the idea behind this method, which I probably don't think I have written, it's called the phenotype risk score, is to extract different phenotypes from the medical record using these billing codes that I talked about before. And then identifying patients who have, looking at each patient and saying which features they have that overlap, right? So up here you can see the top patient there has pectus excavatum, joint dislocation, they got, their lung collapsed and they have a retinal detachment. So they actually look quite a bit like somebody who has Marfan's. And the bottom patient there, they don't have any overlapping symptoms that we ascertained through this. They don't look at all like they have Marfan's. So the phenotype risk score is just meant to kind of mimic this intuition and assign a score. And the way we do that is that it's dead simple. We just take each of the features that's from the Mendelian disease and we weight them based on the log inverse proportion that they occur in our population. So a rare feature like pectus is going to just have a heavier weight than a common feature like, let's say, asthma or something like that would have a pretty low weight. And so then we just sum up those weights, and that's the person's phenotype risk score. So of course, I would be very hypocritical if I didn't test this against, either genetic or otherwise gold standards, and we did a lot of testing. So this box plot here shows that if you take people who are diagnosed with Marfan's disease, they have a phenotype risk score that is, 3 standard deviations higher than what you would expect and compared to matched controls. What this told us is that you can differentiate individuals that are diagnosed with a disease like Marfan's using only the features of that disease. We've since tested this on 16 different diseases. It works very robustly. So last year we put out a paper where we applied this method. We weren't developing this method so that we could recapitulate the diagnoses that were already made, right? That was just our positive controls. What we really wanted to do was look at these rare genetic variants and ask which of these variants are possibly pathogenic. Without getting too far into it, maybe some of you guys know about how much of a problem it is when people are suspected to have a Mendelian disease. They go in to their doctor and they get tested. Let's say they'll get a collagen panel because they look like they have Marfan's. And instead of getting a yes or a no, yes, you have Marfan's, you have this truncating mutation. No, you don't have Marfan's, we didn't find anything. They'll get, oh, there's a weird looking variant, we have no idea what it is. It's a variant of uncertain significance. This is a huge impediment currently to using genetics in the clinic today. And it's a huge burden on patients, it's a huge burden on physicians. One of the reasons that I think there are so many variants of uncertain significance currently is that a lot of these variants have actually been found using family-based methods. So you find a family where there's, looks like there's a Mendelian disease and you sequence them and you identify what the causal variant is, which is like brilliant in its, I love the kind of transparency and logic of that process, and yet it's difficult to scale. So we tried to use the phenotype risk score on a population basis to say if we had a population of people and we knew that some of them carried these rare genetic variants, then we could ask, do people who have this rare genetic variant in FBN1, do they look like people with Marfan's? And if they do, then that is a piece of evidence that can move the probability that that variant is actually causes Marfan's disease. So the paper that we published last year, we used a really small data set, but we recently were able to, with the eMERGE network data, eMERGE, round 4 of eMERGE, we were able to sort of apply this in its pure form in sort of the way that was, apply it in the way it was meant to be applied. So for this eMERGE project, we had 15,000 patients who were sequenced for 109 genes across 9 different clinical sites, including Vanderbilt. And this is the same network where we share phenotype and genotype information across the network. So what I received to do this analysis was just the sequencing data, which is done at Baylor, and it was really good data. It was good sequencing data, and phenotype data that was just in the form of billing codes and some demographics. And I want to emphasize that this is a pretty realistic situation. When you're thinking about collaborating across institutions, if you can come up with a method that only relies on billing codes, you'll have a hell of a lot greater chance of getting somebody else to implement your stuff than if you come up with a very complicated algorithm. And I guess in case I didn't emphasize it enough, sometimes you need the complicated algorithm. If you're going to be looking at sepsis, for instance, or ARDS. I have a sister who's a pulmonologist. She studies ARDS. I'm like, she has the most complicated phenotype to get out of the medical record. You're going to need some complicated rule-based stuff. But if you can get away with using billing codes, then you should, because it's much easier to make your algorithm transportable. So using just this data, FBN1 was one of the genes that was on the eMERGE-seq platform. And so I was able to first look at my positive controls. So what's the phenotype risk score of patients who carry a known pathogenic variant in FBN1, which causes Marfan's? And these are written down as standard deviations here. So you can see people who have pathogenic variants, they have very high phenotype risk scores, meaning they have more aortic aneurysm, they have more high myopia, et cetera, right? On the other hand, people who carry rare known benign variants in this gene basically have normal phenotype risk scores. But then the action happens when you look at a ton of variants of uncertain significance, which is most of the variants that we found in the population. And you can see here that there are a number of variants that look totally fine, and there are a few that look like they're correlated with having Marfan's. So again, this is a method that we're thinking about scaling and using to produce more knowledge about these genetic variants so that eventually when somebody goes to a doctor, and they're found to have one of these, a physician could tell them something more certain than I'll get back to you in 5 years, and I probably won't even get back to you. So that's actually, this is a miracle. I finished early. That's all I got to say, except to thank my awesome colleagues and really thank you for your attention. And if anybody has any questions, I'm open to it.